Hello, everyone, and welcome back. So, a couple of lessons ago, when we talked about matrix vector products, we talked about when you multiply a vector by a matrix, you can think about that as essentially transforming or changing that vector. Because when you multiply a vector by a matrix, what you get is another column vector as a result of that. And in this lesson, we played around and experimented with a couple of different matrices to determine their corresponding effects on vectors. For example, this matrix 4004 transformed a vector by turning it into a vector that was 4 times longer than what it was before, scaling vectors by a factor of 4. So we've said essentially that matrix multiplication can be thought of as a linear transformation. And what we're going to talk about today is that the reverse is true as well. If you have a linear transformation that's turning one vector into a different vector, then you can think about that linear transformation in terms of matrix products. Specifically, if you have a linear transformation T, that's taking n-dimensional vectors and turning them into m-dimensional vectors, then there is a matrix A that has m rows and n columns that has exactly the same effect on vectors as T does. So in other words, if you apply T to a vector V in the domain, you're going to get exactly the same result as if you multiplied V by this matrix A. And so in a situation like this, we would call A the matrix representation of this linear transformation. So for example, suppose that I have a linear transformation and the action performed by this function is to take vectors in two-dimensional space and scale them by a factor of 5. First of all, let's establish the domain and the codomain of this function. The question explicitly says that this function takes in two-dimensional vectors. Because of that, the domain is going to be R2 in this case. And when you scale a two-dimensional vector, when you resize it, the result is going to be two-dimensional as well. So in this case, the codomain will also be R2. So this linear transformation, taking vectors in R2 and producing vectors in R2, can be represented by a 2 by 2 matrix, a matrix with 2 rows and 2 columns. There is a matrix such that matrix multiplication has this same effect of scaling vectors by a factor of 5. In particular, I claim that this matrix here, 5, 0, 0, 5, has exactly the same effect on vectors as the transformation described here above. So to verify that, let's go ahead and take an arbitrary generic vector in the domain, v1, v2. Let's start by applying the transformation v to that vector. V's job is to scale this vector by a factor of 5. Result would be equivalent to 5 times the vector v1, v2. So 5v1, 5v2. Meanwhile, if I compare what I get when I multiply V by this matrix A, 5005 times V represented as a column. In this case, if I do those dot products, I'll still just get 5v1, 5v2, which is the same vector, just written in column notation. So because A times V is the same thing as the transformation applied to V, we could say that matrix multiplication by this matrix A has the same effect on every vector in the domain as the transformation T has. So once again, we use this language. A is the matrix representing the linear transformation T. Every linear transformation can be thought of in terms of matrix multiplication, and all matrix multiplication can be thought of in terms of linear transformations. So essentially, what we're saying is that these two concepts are interchangeable. Matrix multiplication is, for all intents and purposes, exactly the same thing as a linear transformation of vectors. So once again, this is beautiful because what it means is that no matter what linear transformation you're working with, you can take that linear transformation and encode it and think about it in terms of a matrix and in terms of matrix multiplication. And as we've noted several times before now, matrix multiplication is an incredibly efficient data structure. It allows you to do multi-threaded calculations basically automatically. So that's the advantage of taking things and representing them using matrices. And here we're going to talk now about how to take a given transformation and find the matrix that encodes and represents that transformation. So here's the general process for finding the matrix that represents a linear transformation. If you want to find matrix that corresponds to a given linear transformation, you start by applying the transformation to the standard basis vectors E1 through En, for standard basis vectors for the domain of T. And then once you have applied that transformation to these standard basis vectors, the corresponding outputs are going to become the columns of your matrix A, representing this transformation. Let's go ahead and work through this process so that you can see what this looks like in action. I have a linear transformation here, and T's job is to take a vector in two-dimensional space and rotate it counterclockwise by 30 degrees. Let's go ahead and find the matrix that represents this particular transformation. So first of all, let's acknowledge that this particular transformation is going to have a domain of R2 that was described to me. And then after rotating a two-dimensional vector, you're just going to get another two-dimensional vector. So the codomain of T is also going to be two-dimensional. So I anticipate that the matrix that represents this transformation is going to have two rows and two columns. So now we just have to figure out what are those columns of A. And to determine that, we are going to apply this transformation that's been described to us. We're going to apply the transformation to the two standard basis vectors E1 and E2 for two-dimensional space. In other words, we're going to apply the transformation to the vector 1, 0 and to the vector 0, 1. And we're going to see what happens when we apply the transformation to these two basis vectors. Now, if I take, for example, the vector 1, 0 in two-dimensional space, a vector which points one unit in the positive x direction. If I rotate that vector counterclockwise through an angle of 30 degrees, my arrowhead is now pointing to a location on the unit circle. On the unit circle, because the vector's length is still 1 unit, it was just rotated. A location on the unit circle corresponding to an angle of 30 degrees, as measured from the positive x-axis. So the coordinates of the arrowhead will be given by sine and cosine. Cosine of 30 degrees, sine of 30 degrees. So in column notation, the result of applying this rotational transformation to the first standard basis vector would be the vector cosine of 30 degrees, sine of 30 degrees. If I perform the same action on the other standard basis vector for R2, where I have the vector 0, 1 initially pointing straight up, when I apply the linear transformation to this vector, and I rotate the vector through an angle of 30 degrees, I now end up with a vector whose angle with the positive y-axis is 30 degrees. So let's use some trigonometry to figure out where the arrowhead is located in this picture. I'm going to note that if I draw a line over to the y-axis, I form a right triangle in this picture where the hypotenuse of the right triangle is equal to 1 unit. 1 unit because that's the length of the vector. The length of the vector has not changed as a result of this rotation. So now if I think about what sine of 30 degrees is equal to in this picture, just using the SOHCAHTOA formulas, sine is equal to this opposite measurement, this opposite side in the right triangle, this horizontal measurement, divided by the hypotenuse, divided in this case by just 1. Now notice that the opposite side of this triangle is almost an exact match to the x-coordinate of the arrowhead. The only difference is that the x-coordinate of this arrowhead is going to be negative. So because of that, I would say that the x-component of my vector is equal to negative sine of 30 degrees for this arrowhead. Similarly, we can say that the y-coordinate is going to be equal to cosine of 30 degrees. And we would leave this y-coordinate positive because this vector in quadrant 2 would have a positive y component. So what this means is, after applying this linear transformation to E2, we would get the result negative sine of 30 degrees in the first entry and cosine of 30 degrees in the second entry. These are the components of the vector that we've gotten after rotating 0, 1 counterclockwise through this given angle. So finally, to construct the matrix that corresponds to this rotational transformation, all we have to do is take these two column vectors and use them to build a 2 by 2 matrix. The first column in the matrix is going to correspond to the result of applying t to the first standard basis vector. So the first column of A is going to be this result, cosine of 30 degrees, sine of 30 degrees. And the second column of A is going to be this second column vector, negative sine of 30 degrees, cosine of 30 degrees. So this would be the matrix representing this transformation. If I multiplied vectors by this matrix, it would have this identical effect of rotating vectors through an angle of 30 degrees. This matrix, when multiplied, would perform that same rotation. You might recognize this sort of format for a rotational matrix from our lesson on matrix vector products. When we did our lesson on matrix vector products, we saw that if we had a matrix whose first column was cosine 45 degrees, sine 45 degrees, and if its second column was negative sine 45 degrees, cosine 45 degrees, then the matrix with those columns had the effect of rotating vectors counterclockwise through a 45-degree angle. So in this problem, we were given the matrix and we wanted to understand what transformation that matrix was creating. Whereas in this lesson, we're doing essentially the opposite. We're given the transformation, we're given the action that needs to occur, and then we're trying to find the matrix that would cause that action to happen. Now, just a quick note about why this particular method gives rise to the matrix that's representing a linear transformation. Why does it work to fill the columns of A with these output vectors? So to explain that, we know that by definition, The matrix representing T has the following property. If you take a vector and multiply it by this matrix, the result is the same as if you took that vector and applied the transformation to it. This has to be true for all v's in the domain. If it has to be true for all of the v's in the domain, then in particular, it has to be true for the standard basis vectors in the domain. So for example, A times E1 has to be the same thing as TE1. A times E2 has to be the same thing as T applied to E2, and so on and so forth for all the standard basis vectors of your domain. Now let's think about what happens when I multiply a matrix, for example, by the first standard basis vector. Just as a quick example, let me suppose that I multiply this first standard basis vector by the matrix 2, 3, 4, minus 5. If I follow through on this matrix multiplication using the typical dot product formula, the result is going to be equal to 2 in the first entry from the first dot product, and 4 in the second entry from the second dot product, which, notice, has given you back exactly the first column of the matrix A. Similarly, if you multiply a matrix by the second standard basis vector, 0, 1, when you go through with that dot product calculation, what you end up with is exactly the same thing as the second column of the matrix A. So in conclusion, T applied to E1 must be the same thing as A multiplied by E1, which is the same thing as the first column of A. And that's why we set the first column of A to be equal to whatever the transformation returns after we apply it to this first standard basis vector. Likewise, T applied to E2 must be the same thing as A multiplied by E2. And so that must be equal to the second column of A. And so that's how we decide that the second column of A should be filled in with whatever we get when we apply the transformation to the second standard basis vector. Let's do one more example of finding the matrix corresponding to a given linear transformation. Let's go ahead and consider this transformation T applied to a three-dimensional vector xyz. It takes that three-dimensional vector with those entries and reflects it over the xy plane. So as a result of that reflection over the xy plane, the z component of that vector becomes the opposite of whatever it was before. So first of all, let's verify that the function defined here is an honest-to-goodness linear transformation. Let's make sure that this is a linear transformation as opposed to a non-linear transformation. And so to that end, I'm going to write down a couple of arbitrary inputs for this function. I will call A equals x1, y1, z1. I will call B equals x2, y2, z2, and I will let C and D be any real scalar. And I'll consider what happens if we use the order of operations of combining the inputs first and then applying T to that result. Now, following PEMDAS, working from the inside out, the first thing that I would do is the scaling and the addition on these inputs inside of the function t. So this would give me, after simplification, cx1 plus dx2, cy1 plus dy2, and cz1 plus dz2. This would be the combination of the inputs. Now, if I apply t to that, t's job is to take the last entry in the vector and turn it into the opposite of whatever it was before. So in this case, the result of applying t to this vector would be the first entry doesn't change, the second entry doesn't change, but the final entry becomes the opposite of what it was before. So the final entry becomes negative what it was before, turning that positive CZ1 into a negative CZ1, turning positive DZ2 into the negative version of that. Let's go ahead and do the combination with the other order of operations. So meanwhile, let's go ahead and apply t first to the inputs and then combine the outputs. Now, once again, t's job is to take the final entry in the vector, to take the z component and make it negative. So now if I use vector scaling and addition, this guy turns into cx1 plus dx2, cy1 plus dy2, and then negative cz1 plus negative dz2. And so what we can see is that after simplification, these two results are exactly the same. So because we were able to change the order of operations and get exactly the same result, that's proof that this particular transformation is truly linear. Because of that, there is a matrix that represents this transformation. So let's try and find that matrix that has that same effect of reflecting vectors. To do that, all I need to do is apply this transformation to the three standard basis vectors of the domain. If I take the vector 1, 0, 0 and apply this reflection, then the result will be exactly the same thing as I started with, because applying a minus sign to the 0 in the third entry won't change anything. Something similar is true when we apply the transformation to the second standard basis vector for 3D space. A negative sign will hit this 0 in the third entry, and that won't affect anything. But when I apply the transformation to E3, this will have an effect of turning the 1 in the z component into a minus 1. So having now found these three results, let's use them to form the three columns of our matrix A. So this matrix here would be the matrix representation of this transformation. Multiplying vectors by this matrix would have the same effect on vectors as t. It would have the effect of reflecting vectors over the xy plane. So that concludes today's lesson. In today's lesson, we learned that a linear transformation could be represented via multiplication by a certain matrix. The matrix representing a linear transformation can be found by applying the transformation to the standard basis vectors for the domain. The result of applying the transformation to the standard basis vectors create the columns of the matrix A that represents your transformation. So, in the end, you can think about linear transformations of vectors as being essentially the same concept as matrix multiplication of vectors. Every instance of matrix multiplication is a linear transformation, and every linear transformation can be represented via matrix multiplication. So these two things, even though they might seem different, in the end are the same.